Hey, you guys. Well, I finished grading your fun sheet quiz, and you didn't too bad overall, but let's go over it real quick, and hopefully this will help you prepare for the exam. The whole theme was ammonia and reaction of ammonia with water. So the first thing I asked you to do was write the equation. So let's do it together. Ammonia is NH3. Now, nobody got this wrong because it was on the board. Now, I could have put gas there, but I put aqueous. And anyway, I go ahead and react it with water. I put an equilibrium arrow, and I have ammonium aqueous plus hydroxide. And I asked you, should this have been an equilibrium arrow? Now, I think almost everybody said yes, and it should be, but your reasonings were kind of strange because you were just saying things like, well, because it's an equilibrium. Well, because if something is going in a forward direction, it has a reverse direction. Kind of all true, but at the same time, if something is in an equilibrium, the reason is in an equilibrium or is doing something like that is kind of like the which side game. I mean, it's not like there's a stronger side than the other. Now, what dictates, and what describes how much of each side is the equilibrium constant. The equilibrium constant for this is a Kb, and that one was equal to 1.8 times 10 to the minus 5. So according to that tiny number, it's mostly reactants. So not because it's products over reactants. So the main thing I was looking for, and I was thinking everybody was going to say, well, it's a weak base. And if it's a weak base, then it doesn't react completely. And there is some equilibrium. So anyway, let's move on. So we have a titration. Titration was bringing together all these different concepts. So we had our 10 milliliters of 0.3 molar ammonia titrated with a 0.1 molar ammonium hydrochloric acid solution. And then I said calculate the pH of the 0.3 molar NH3 solution. So this was the bucket or the Erlenmeyer flask, however you want to look at it. And there was 10 ml in there, and it was 0.300 molar ammonia. So we haven't added any hydrochloric acid, so then we could think of it like this equation up here, and we could apply an ice table to that. And if we did that, I'm going to write it over here so we can put the ice table underneath it. Your initial would be 0.300 molar, and then the ammonium hydroxide would be at 0. So you got to kind of think of, if I bubble through some ammonia gas through here, or initially there's 0 of ammonium and hydroxide until the reaction occurs. Now there's a K with this. These guys are going to, the ammonia is going to decrease by a certain amount. The other two are going to increase to the tune of XX and 0.30 minus X. So the question is, what's the pH? So if I want the pH, I need that, and that means I need the K. The K was 1.8 times 10 to the minus 5. I set that equal to x squared divided by 0.3 minus x. Throw out the x, and I believe you guys got, this is solving for x, which is an OH, and the OH concentration, if you do this way, is 2.3 times 10 to the minus third, something like that, 0.0023, and then we take the minus log of that number. I got my calculator now. And then we take the minus log 0.0023, we take log negative, and we get POH equals 2.64, but that's the POH, so minus 14, and we get 11.36, and that was the pH, 11.36. Check. Okay, indicate the equivalence point on the graph and calculate the pH at the equivalence point using the molarity of the conjugate acid. Now, there was a little bit confusion about where the equivalence point is. The equivalence point, if you draw a line, a vertical line, right down through the most vertical portion, that's the equivalence point. But then we say, well, what's the pH at the equivalence point? That's the equivalence point in like milliliters. But the equivalence point pH is that kind of center, not at the top, not at the bottom, right in the middle. So there was a little bit of confusion with that, but you know, that quiz was helping you learn. So anyway, now this is, I marked the pH 5. It's supposed to be like 5.13, but from this graph you might say 5.2, and that would be okay. Indicate the equivalence point. Calculate the pH at the equivalence point. Now, you can see the pH at the equivalence point, but the idea is to say, well, now calculate it. Well, what's an equivalence point? Equivalence point is when all of it has reacted. So remember when we were doing those equations or those reactions, adding the hydrochloric acid, starting moles, change in moles, and ending moles. When we did this, we had molarity times volume, and we got 0.003 moles. At the equivalence point, we must add the same amount. That is the take-home message of the equivalence point. At the equivalence point, the same amount of moles has been added of titrant to equal what was in there. Now, we knew what was in there for this one. So our products here are ammonium and chloride, and we can say 0 and 0. Ending, since we're adding the same amount, we have to take away that 0.003 from both sides, and then you have 0. And then you must have created, remember stoichiometry, it's all 1 to 1 there. You must have created that. We're not going to worry about the chloride spectator. It's not going to react with water at all. It's a neutral part of a salt, like we learned in our lab. So anyway, this is the molarity. That's the moles. To get molarity, we need to divide it by the V total. That's when the V total comes in. Now, there's two things you could have done here. You could have just remembered that you started with 10 ml of the solution, and you added 30 ml to get to the equivalence point. But say you didn't remember that. Well, how do I know? I can take this volume of HCl, moles of HCl. I know the molarity of HCl is 0.100 moles per liter. That's the molarity. And I want to know how many liters do I need to deliver 0.003 moles. Well, I can take my 0.003 moles and use the molarity as a conversion factor for every, it's moles per liter, so it's 0.100 moles per 1 liter. So if I do that math, it turns out to be 0.030 liters, which equals 30 milliliters, and that's where that one came up there. The total of those is 40.0 milliliters. Why am I doing this? Because I needed the V total, so I could divide that into the moles of ammonium, so I could determine the molarity of the ammonium, so I could calculate the pH of just the ammonium solution that was created at the equivalence point. So let me get rid of all this stuff, because since we're at the equivalence point, I now have a new scenario going on, and that new scenario is the only thing that's in the bucket now is the ammonium that I created by the titration or the neutralization. So now this ammonium is going to react with water, and we are going to get ammonia plus hydronium, which is going to give us a certain pH. So we go through the ice table. Now, I didn't finish it, but remember there was 0.003 moles of ammonium divided by the total volume, 0.040 liters, and this turns out to be 0.075 molar. That was created in the bucket. As soon as that was created, you would say, well, there wasn't any of those like we normally do. Minus x plus x plus x. But now, since this is the conjugate acid of ammonia, we are not going to use the Kb, we're going to use the Ka. The Ka for this is 5.6 times 10 to the minus 10. Now I go through kind of my same thing, and I figure out the x, and I can figure out hydronium and pH. So 5.6 times 10 to the minus 10 is equal to x squared divided by 0.075 minus x. Throughout the x, you solve for x, and you just keep going, and then your x is going to give you that. Minus log of that will give you pH, and it should be close to 5.20. So anyway, yes, that's how that did work out. All right, so let's keep going. The next one was indicate which area constitutes a buffer. And there was a little bit of confusion on this one too. Now the buffer region should kind of be in this area. Initial pH was right here in the beginning at a tiny bit of acid, and it plummets. If you look at that change right there in the beginning from initial pH and that to that first point, it's steep, but then it levels off. And I asked you, how do you know it's a buffer? And I said, explain. Well, what is a buffer? A buffer is a substance that resists changes in pH. That's true, and a lot of you guys said that. But it also is something that has concentration of acid and the conjugate base, or concentration of base and its conjugate acid. Now in our situation, we had base and conjugate was being created as the titration was going on. So all along in this area, you have some of both, and it's buffering or resisting changes in pH. So this whole region here is a buffer region until you are used it all up, and then you get to a point that now I add one more drop of HCl and the pH plummets because there was nothing there to buffer it. There is no buffer down here as far as I know because you're just continuing to add HCl. So there's no way to regenerate. The only thing that's in the solution at that time after you've reached the equivalence point would be ammonium. And then if you kept on adding HCl, yeah, you add more chlorides, you add more H pluses, but never is there any ammonia, NH3. Therefore, it cannot be a buffer area. All right, check. All right, and then our last area, well, it looks like I lost that last slide. But either way, we were pretty much finished with that. The last one was explain the position of the equivalence point. Why is it not 7? So when we say, why is it not 7? At the equivalence point, there is only conjugate whatever. In this case, it was conjugate acid. And that acid then reacted with water to create hydronium because that conjugate acid came from a weak base. And that weak base makes a strong conjugate acid compared to water and therefore makes a acidic solution. So anyway, that's really all there was to that question. And it looks like that was, I don't know, I might have flipped through another slide too quickly. We're on slide 3, which is actually, I missed the determine the Kb of ammonia from the graph, and from the graph, calculate the molarity of the ammonia solution. So let's calculate the molarity of the ammonia solution given this graph. I asked you to do that, and at the equivalence point, which is about 100 mils of HCl added, that's the equivalence point. So I know the molarity, so this is volume, I know the molarity of the HCl, and that means I can get the number of moles of HCl added at the equivalence point. If I know the number of moles of HCl at the equivalence point and I know it's 1 to 1, that's equal to the number of moles of the ammonia that were in the solution. Now on the previous question I said, well, it was a 50 ml sample. That's equal to 0.050 liters. So if I get the number of moles from the titration up here, and then I can divide it by the liters that was in the sample. So just remember to use what's in the sample. So anyway, that's a molarity calculation from a titration data, and that's very similar to your lab. So just review that because I'm sure you're going to see one of those on the exam. All right, so that was that problem. That was like number 3, the second number 3 on the quiz. Then we go to the next question, which was determine the Kb of ammonia from the graph. Well, now if I look at this graph, I have an equivalence point. I have an equivalence point right there at approximately, you can say 100 mils. What's half of 100? 50 mils. So I run over to the 50 mil area and I draw hopefully a better straight line. And wherever I hit right there is the half equivalence point. And then the pH at the half equivalence point, pH equals pKa at the half equivalence point. So you got to remember that, and because that's a very useful piece of information, especially with weak acids and bases being titrated. Okay, so now that we know that, I can go pull that number, 9.2-ish, is the pH at the half equivalence point, so I can set this equal to pKa, and then I can solve for Ka. Now what's strange, as you might think, and I struggled with this too, and I still do a little, is that the pH is equal to the pKa at the equivalence point. Why is this true when we're titrating a base? That this is a base. I mean, it seems strange, but it doesn't matter, because let's plug in the numbers just for fun. If you have 9.20 equal to pKa, now get the Ka. Remember remember pKa is the minus log of Ka. So then if I solve for Ka, I put in 9.2 in my calculator, put a negative sign on it, and hit inverse log. And I get 6.31 times 10 to the minus 10. And sure enough, this is very close to the Ka of ammonium, which if you look in your book is 5.6 times 10 to the minus 10. See how close that is? So that's the Ka. Now I ask you to get the Kb. You actually now have to solve for that because Ka times Kb equals Kw. So you pop the K in there. Kw is 1 times 10 to the minus 14. And then you can solve for Kb from that. Now this is like an experimental Kb, so it's not going to be exactly the same as the one on those tables. So when I asked you to do that from the graph, that's what I was thinking, is that you would say, oh, I know that pH is equal to pKa at the half equivalence point of a weak acid, right? Or base, and then I can get my Kb by using that other relationship. Now I did play around, and I did find, and I was thinking, well, what about, can I do it this way? If pH is equal to pKa at the equivalence point, what about pOH is equal to pKb? And it did work. So anyway, it just seems weird. So I don't know, but you have to do pOH. This was pH, and pH is 9.2. pOH is 14 minus 9.2, and that's 4.8. 4.8 is pOH is equal to pKb, which is minus the log of Kb. So then I just solve for it. I put the negative on the 4.8, take the inverse log, and there you have it. I get a Kb equal to 1.6 times 10 to the minus 5. And if you remember, the Kb, the literature one in our book for ammonia, is 1.8 times 10 to the minus 5. So our literature one, our experimental one from this is not so bad. Anyway, I'm going to keep moving because I know I don't want to keep it too long. Let's go to this question about the indicators. I thought this was kind of fun because I was like, oh, let's go look at the table. The table has indicators. What would be an effective indicator, a good indicator? Now I asked you pick an indicator in which the color would be orange at the equivalence point. Okay, well the equivalence point is 5.1-ish. So that means I need something over here that changes in the 5.1 range, maybe. You can, and I wanted orange. Now I said there's orange here. But remember, red plus yellow equals orange. So if you have a mixture of them in solution, it might look orange. I wonder if we could do that on here. Highlighter. If I put yellow, and then I go highlighter, and I put red, and I overlay them. Nope, it doesn't work. I was going to see if it would overlay them. Let's put red first, and then put orange on, yellow on top. Nope, it's not working. So it's not being like transparent watercolors. It's being like opaque or acrylics where they just lay on top of each other. Well, anyway, I was just trying it. But so on the on this table, I said, well, where's it going to be orange at the equivalence point? Well, we have red and yellow. Here's red and yellow. Right in the middle makes orange. But this guy would be orange less than 2.8. So it would be orange like down here. And then starting here, it would be red all the way up. You see, so that's not a good one. How about another red and yellow that I have? Let's see. Let's go to red and yellow. Here it is. Red and yellow is methyl red. 4.2 to 6.3. So that means above 6.3, it's yellow. So maybe up here. Above 6.3, it's yellow. And then below 4.2, it is red, which is down here. So you see, if you had a mixture, you could be orange. I was thinking methyl red. That's the one I was going for. But you could have said chlorophenol blue if you really wanted to. Yeah, that one would have worked also, because 5.1 is kind of in the middle of there. But I don't think, some of you guys were picking like bromothymol blue and stuff. I don't see how, because there's no yellow and red to make orange if you were in the middle. But on cresol red, you might have chosen, because there's orange in the middle. But, you know, I'm not sure. If I look at this, if I say, well, below 7.2, it is yellow. So 7.2 is kind of up here. So it's yellow down here, and then it's red up there. Well, I mean, if you hit it and we're on the downswing and it was yellow, you might, yeah. I mean, you could have chosen that one if you wanted to argue that. So anyway, as long as you argue it with making sense. All right, so that's the indicator stuff. I'm going to stop this video right here before I go on to the KSP stuff to make another video for that.